So far, we have learned how to solve quadratics using graphing and using factoring. And both of those methods are good methods. However, they both have significant limitations. When we are graphing, the limitation is that you can only give rational answers if you want exact answers. So they either have to be numbers that are whole numbers or integers, or numbers that can be turned into fractions to be given exact answers. And those same kind of answers are the same limitations for factoring as well. There's a whole another set of numbers that could be solutions. We could have irrational numbers that are solutions, and we could even have imaginary numbers that are solutions. And that is something that we haven't discussed yet. And before we get into the other methods that can find those imaginary solutions, we need to find out what imaginary numbers are and how do we deal with them. So that's what this video is about. You may want to pause the video to go ahead and write this down. Like I discussed just a moment ago, when we are graphing, we could always tell what the real solutions were because we were looking for the x-intercepts. However, when we have something that looks like this, it doesn't have any x-intercepts. The intercepts don't exist and therefore there are no real solutions, but that doesn't mean that there are no solutions. There are actually two imaginary solutions. And imaginary numbers happen when there is a negative underneath the radical. When we have a negative number underneath a square root, we get I in our answer. And that's our imaginary numbers. Imaginary numbers actually have quite a bit of application, especially looking into electrical engineering and things of that sort. But for what we will deal with, we are just going to really focus on when I is underneath a radical, or sorry, when a negative number is underneath a radical. We also need to be able to learn how to add and subtract those imaginary numbers and how to multiply them. We're also going to deal with how to simplify them as well. In order to help us do that, I have a little song that kind of speaks about how we would simplify imaginary numbers. Um, so I'm going to go ahead and sing it. I am self-proclaimed not a great singer. However, I'm hoping that this song will at least help you remember some things. So here we go. I'll teach you everything I can. I'll grade your tests with these two hands. We'll hang some hundreds on the wall. And when the parabola's in the air, you won't have to ask if I still care. 'Cause when we're finding the roots, I know that you'll find them all. I squared always equals -1. I squared and I cubed always equals -I. I cubed. And what's really fun, 'cause it's equal to 1. I love math with every beat of my heart. It's I for. All right, so now that I have significantly embarrassed myself, and I'm kind of glad we won't be face to face when this happens, although I do it every year. I significantly embarrass myself by singing this to you guys. But my hope is that that embarrassment is not in vain and that will actually help you remember how to simplify I. Now, I in itself is the imaginary number part, and we call that the pure imaginary number when it just has I in it. And that happens whenever we have a negative number underneath the radical. For example, if I had the square root of negative b squared, I could split that out into b squared times the negative 1. And this square root of negative 1 is what changes to I. Okay, and that's the imaginary part. Now, imaginary numbers can be paired with real numbers. And when that happens, we call them complex numbers. We put the real number in front and we add the imaginary part. These two are not like terms. They can never be added together. You need to treat that I term just like it was a variable where you had, 1 plus 6x. You would not be able to add those together to make 7x. They would have to stay separate. That's kind of how we will treat the I in terms of being able to combine like terms or not. The next two will help us be able to both solve some of our square roots or our quadratic equations with square roots. And this one will help us be able to simplify when I is in the denominator. The square root property happens when we take the square root of both sides to solve an equation. And that can happen whether or not there is an I in the equation. Complex conjugates. When we have I in the denominator, we need to get the I out of the denominator. It's not considered simplified until that I is out of the denominator. This means that we will need to use the concept of a complex conjugate. A complex conjugate happens when we have the same numbers, but they have opposite signs. And we can use that, like I said, to simplify the quotient of two complex numbers to get that I out of the denominator. We'll see examples of that later on. For now, let's take a look at how do I simplify some of the powers of I. Now, this first one is kind of a one-way street. We will never take I and simplify it to this. We will, however, take this and always simplify it to I. And that is that I is the square root of negative 1. Like I said, we will never take and move I to be the square root of negative 1, at least not in this class. But anytime that you have a negative underneath the radical, you will always change it into I. So I guess I need to change that arrow to make it make a little more sense. You will always change square root of negative 1 to I, but never changing it the other way around. Now this I squared. If you think back to that embarrassing song I did just a moment ago, or look back up at your lyrics if you took mercy on yourself and pressed mute during that. But I squared always equals negative 1. So whenever you have anything that's I squared, you need to be able to simplify that to just be negative 1. And the reason for that, I'll kind of show you the reason over here, my little thought bubble, is if I is the square root of negative 1, and I squared would be I times I, then that would be square root of negative 1 times square root of negative 1. And we can take those, which are both i's, which would be I squared, which simplifies down to just negative 1. I cubed. Why is that negative I? Well, it's negative I because we have I squared and one more I. That would equal I cubed. We know that I squared is negative 1, and I still have an I hanging out here. That's why I cubed is negative I to the fourth. Well, I to the fourth would be the same thing as having I squared and another I squared. Well, I squared equals negative 1. Another I squared equals negative 1. Negative 1 times negative 1 gives me positive 1. That got really blurry. So that is the end of our I song, but there's so many other exponents that I need to be able to simplify. Well, you should be able to start recognizing a pattern as we work through these. But even if you don't recognize the pattern, or sometimes it's a little too long to run through the pattern to get there, you can always use the pieces that we learned from the song to simplify I of any exponent. For example, I to the fifth can be rewritten as I to the fourth, and then one more I. We know that I to the fourth equals 1, and then there's another I. So that means that I to the fifth is 1I, or just I to the sixth can be rewritten as I to the fourth times 2 more I's. We know that I to the fourth is 1, and I squared always equals negative 1. 1 times negative 1 is negative 1. So I to the sixth is negative 1. I to the seventh, that can be rewritten as I to the fourth. And I'm using I to the fourth because that's the largest one from the song that I had earlier. You could use I squareds if you only ever remember that I squared always equals negative 1. You could use I squareds repeatedly, in which case you would need 3 sets of I squareds and simplify that way. But if you remember the whole chorus, you can use your I to the fourth, which kind of significantly cuts in your time there. I to the fourth, and I would need 3 more I's to get to 7. I to the fourth we know is 1. I cubed always equals negative I. 1 times negative I is negative I. How about I to the eighth? That's I to the fourth, and I still need another I to the fourth, which means I have 1 and another 1. So I to the eighth simplifies down to 1. And if you look back, we can follow this pattern. I, negative 1, negative I, 1. I, negative 1, negative I, 1. That means that this should simplify down to be I. Let's use our same technique here of using our I to the fourths. I to the fourth. I've still got 5 more I's to go, so I need another I to the fourth. I've got 1 more to go, so I've got another I. I to the fourth is 1, I to the fourth is 1, and then I've got an I left out. So it does simplify down to just I. You can do that to simplify any exponent for I. In fact, let's flip the page here. And let's do I to the 40th and I to the 63rd. Now, I think it can be quite tedious to write out I to the 4th, I to the 4th, I to the 4th 10 times when we know that they all equal 1 and it's not going to matter. So we can use a little bit of a technique here of division in the remainder system, like what you learned when you first learned how to divide back in elementary school. We know that I'd be taking I to the 4th cell, because that's the largest I that I know from the song, and it also helps me because I to the 4th is just 1, and so it doesn't change anything that it's multiplied by. What we care about is how many I's were left over when I'm done taking out all the I to the 4ths. So to simplify that process, we would take our exponent of 40 and find out how many I to the 4ths could I take out. So we'll divide 40 by 4. 40 divided by 4 is 10. So I'd have 10 I to the 4ths all laid out over here, which you don't have to write. I'm just trying to help you visualize it. So I'd have 10 I to the fourths all laid out here. And all of those simplify to just 1. And I don't need any left over because 10 times 4 is just the exact 40 that I needed. But all of these guys are going to simplify to 1, which means I to the 40th simplifies to just 1. But this right up here kind of helps save. I didn't have to write out all of this. But that's what this was doing. It was saying how many I to the fourths can you take out and how many are remaining. Since there were none remaining, I didn't have anything else left over here. Let's see what happens though when I to the fourth, I can't take an even number of them out. So 63, how many I to the fourths can I take out of there? 4 into 63, it goes 15 times. And there's a remainder because 15 times 4 is 60. I need a remainder. There's still 3 i's hanging out there. So that means I to the 63rd, after I take out all of the I to the fourths, I'd still have I cubed left over. Well, lucky for us, our song covers I cubed. I cubed equals negative I. So I to the 63rd is also negative I. What else can we do with I? Well, I told you before that we deal with I whenever we have a negative underneath the radical. Well, all 3 of these problems have a negative under the radical, so let's see how I comes into play. Square root of negative 81. Well, if it was just square root of 81, it would be really easy. It wouldn't be an algebra 2 problem, but it'd be really easy. I would know it's 9 and I can move on with my life. But it's square root of negative 81. Well, we need to break that down into the square root of 81 times negative 1. That's the same thing. I took the negative 81 and I broke it down into a positive part and a negative part. You can break that down even further and give them each their own root, their own radical. Square root of 81, which we said we knew, is 9. And then I have the square root of negative 1. The square root of negative 1, we learned way up there, is I. So the square root of negative 81 is I. The way that you can always remember it, so whenever you see a negative underneath a square root, it comes out as I every single time. So the square root of 32, we're going to have something similar happening here. We're going to have the square root of 32 that we'll have to deal with. Then we're also going to have the square root of negative 1. The square root of 32 is a little actually trickier. It's something that you should have been more familiar with back in geometry when you were dealing with simplifying radicals. But it is a little trickier. We have to actually do a factor tree here. So that's 8 and 4. 8 can be divided into 2 and 4. 4 is 2 and 2. And here's another 2 and 2. And remember, you are looking for pairs. So I have a pair of 2's to come out. There's another pair of 2's to join it. And this 2 is just hanging out all by himself. So he has to remain inside the radical. So this actually simplifies down to be 4 square roots of 2. And I've still got this negative 1 here. Square root of negative 1, we know that that's I. Now how you would incorporate I into your answer here is it actually is going to come right after that 4. Before the square root. 4 I square roots of 2. We don't want to put it at the end because we might be mistaken to have the I underneath the radical, and we always like to have the number in front of the I. What about this last one? A lot of people get confused and try to take negative 24 multiplied by negative 18, and they're like, oh, that's a positive. There's no I to deal with. But there is an I. You can't make it go away by multiplying them together. Instead, we are going to deal with each of these on their own. That means that we're going to need to take that 3, and he'll be joining us down at the bottom here. And this 24 is going to be broken up. Now this guy, he's going to join us down the bottom. Remember I said that whenever we have a negative, he joins us as I. So I got to break the 24 down. 3 and 8, 2 and 4, 2 and 2. Over here, this 2, he's going to go to the bottom. This negative is going to join us as I. And if you still want to write it out as square root of -1 and then take it as I, that's fine too. Then the 18, 3 and 6, 2 and 3. Now, what we are looking for now that we've broken down the positive parts is we are looking for pairs. And you can look at any combination of pairs that you want. So, for example, we have this 2 gets to come outside and join the 3 and the I. These 3's get to come outside. But we can also take the combination of this 2 and this 2 and combine them together because we are multiplying after all. So this 3 came from down here, the I came from the negative, the 2 came from the negative, the I came from the negative. Sorry, the 2 came from the 2. And then these 2 2's and the 3 were pairs that came out of the radical. Now what's left underneath that radical? Well, there's nothing left here, and here is just a 3. So let's multiply everything that happened in front. 3 times 2 times 2 times 2 times 3 gives me 72. I times I gives me I squared. And I squared always equals negative I. So, oops. Oh my goodness. It's a little late where I'm doing this. I squared always equals negative 1. I squared should equal negative 1. So we have negative 72 square roots of 3. Let's turn it over and see what else we can do with I. What happens when we are multiplying pure imaginary numbers? When you're multiplying numbers with I in them, you will multiply the number in front, negative 3 times 4, negative 12. I times I squared. I squared always equals negative 1. So we have negative 12 times negative 1. So that should equal positive 12. What about adding and subtracting complex numbers? We know this is a complex number because it has a real part and an imaginary part. When you're adding and subtracting complex numbers, you will add together the real parts, negative 1, negative 2, gives me negative 3, and you'll add together the imaginary parts. So 5i plus negative 3i gives me 2i. And that's it. When you are subtracting, I really suggest that you go ahead and distribute that negative to both of the numbers in here so that you can just worry about combining them together, because I see a lot of people that forget that they are subtracting halfway through. So 7 and negative 1 would be my real parts. They make 6. 4i and negative 2i, those are my imaginary parts, and they make 2i. How about multiplying? When we are multiplying things that have I, I really encourage you guys to use the Punnett square method. So you're going to draw a 2 by 2 box, and 6 minus 8i and 9 plus 2i will be multiplied together. It looks very similar to kind of reversing what we did when we were factoring. That's by design. Remember, factoring really means to undistribute, and that's what we're doing here. Is we are now distributing, so we are undoing the factoring. 9 times 6 gives me 54. 9 times negative 8, negative 72, and we have an I. 6 and 2 is 12. 2 and negative 8 gives me negative 16. Whoopsie, I forgot my I here. And 1 I and I gives me I squared. Remember, I squared always equals negative 1. So I have negative 16 times negative 1. That means that this is really positive 16. So when I go to combine my like terms, the 54 and the 16 become like terms now, which gives me a total of 70. And then 12, I forgot my I. 12i and negative 72i combined together to be negative 60i. Let's take a look at this one. I'll attempt not to forget my i's this time. And it really doesn't matter whether you write the negative 2 plus 4i on the side or whether it went on top, as long as they get written on the outsides. So let's go ahead and multiply. Negative 2 times 3 gives me negative 6. Negative 2 times 2i, negative 4i, 3 times 4i, 12i, and finally 2i times 4i gives me 8i squared. I squared always equals negative 1. So this becomes negative 8. Negative 6 minus 8 gives me negative 14. 12i minus 4i gives me 8i. Now this has been a building progression here. We first learned to multiply things that had I. Then we learned how to add and subtract them. Then we learned how to multiply and then add and subtract. So finally, it's all been building up to using these to simplify what happens when we have a quotient with imaginary numbers. That's when that complex conjugate comes into play. We are not allowed to have I in the denominator of our answer. So to get rid of I in the denominator of our answer, we multiply both the top and the bottom by the conjugate of the bottom. So this becomes 4 minus 2i that I multiply by. We never do anything with the conjugate of the top. It's always the conjugate of the bottom that gets multiplied on top and bottom. And the reason why we are able to multiply it by this is because this right here does not change the value of what I started with, because this, the same number on top and bottom, is really 1. It's the same concept as taking, say, something like this and rewriting it as a similar fraction by multiplying top and bottom by the same number. These two simplify to be the same thing. They are the same amount. I didn't change anything by multiplying top and bottom by the same amount. That's what's happening here as well. So let's go ahead and multiply these out. We need the Punnett square for the top and the Punnett square for the bottom. So here's the top, 3 minus I, 4 minus 2i, and then the bottom, 4 minus 2i and 4 plus 2i. So let's multiply them. 4 times 3, 12. 4 times negative I, negative 4i. 3 times negative 2i, negative 6i. Negative 2i minus I gives me positive 2i squared. I squared always equals negative 1. So that makes this really negative 2i. 2. So I have 12 minus 2, which gives me 10. Negative 6i minus 4i gives me negative 10i. That's the top. Now for the bottom. 16, negative 8i, positive 8i, and negative 4i squared. I squared always equals negative 1. So this negative 4i squared becomes positive 4. No I. So 16 plus 4 gives me 20. 8i minus 8i cancels, and we have no I on the bottom. That will happen every single time you multiply a number by its complex conjugate. All of the i's will go away, and you'll be left with only real numbers, which is what we need for our answer to be simplified. You're almost done, but just one more thing. 10, 10, and 20 can all be divided by 10. So my final answer should be 1 minus 1i, or just I, over 2. That's my final answer. Let's do it one more time. Top and bottom will need to be multiplied by the conjugate of the bottom. So that would be 5 minus 6i. That's the only difference between the number that was on the bottom and what I'm multiplying by. So we'll need a Punnett square for the top and 1 for the bottom. There's the top. And the bottom. So multiply the outsides to get the insides. Understanding how this Punnett square works is going to be really helpful when we move into chapter 5 and we start dividing polynomials. So I really encourage you to use this method and get comfortable with it. I've got an I squared, and we know that I squared always equals negative 1. So negative 6i squared becomes positive 6. 10 plus 6 gives me 16. Negative 12i plus 5i gives me negative 7i. Let's multiply for the bottom now. 25, 30i, negative 30i, and finally negative 6i times 6i gives me 36, negative 36i squared. I squared always equals negative 1. Positive 36 is what it becomes. So let's combine our like terms. 25 plus our 36 gives me 61. And then negative 30i plus 30i, that cancels out. So I'm left with 16 minus 7i over 61, which does not simplify because there's not a number that 16, 7, and 61 can all be divided by.